Let's get started today. So today's a Tuesday. We'll just be going over our chapter readings and the material. We'll go through the exercise there. I brought some playing cards because there's a little activity in the exercise where we get to play with cards. So we'll do that today. Quick reminder, tomorrow is Community Day, so there are no classes.
We got the wrong bag.
Okay. So again, no classes tomorrow. So hopefully you're volunteering somewhere. There's lots of good reasons to volunteer. I think one of the best reasons to volunteer is simply self-service. It makes, or self-centered, it makes you feel better. So if you want to feel better tomorrow about yourself, just volunteer. There's some place you can sign up. And one place we're still looking at things is the Duluth Makerspace. We're just going to that community nonprofit and helping them clean and organize their workshops tomorrow from 10 until noon. We'll have some food at noon. There's rides down there if you want. We're still looking for 2 or 3 people to sign up. So if you want to do the self-centered thing and volunteer to make yourself feel better tomorrow, consider that. Some of you are already volunteered and I like to see that. Okay, so that's tomorrow. Let's jump into today. I'm gonna move, I just posted the readings. I'd forgotten to update that. So I'm gonna move that up here to the top. Okay. So this week, we're really talking about operating systems and how operating systems work for things. And what do operating systems do for us? So we're going to look at 2 different chapters here of our textbook. First, we're going to look at chapter 5 of the textbook. We started chapter 5 last week, and we're looking at device drivers and BIOS and these low-level things that start up here. But about halfway through, it switches to operating systems, and we kind of stop there. So this week, we're going to talk about operating systems and what they do. There are a couple of different types of operating systems. The main breakdown is often real-time versus non-real-time operating systems. And we don't really deal with real-time operating systems. Real-time operating systems are generally running machinery or like a robot or something like that, that has to work in the real world and work in what we call real time. So like if your computer slows down a little bit every once in a while, that's, you just kind of wait and for it to do what its job. So if it slows down a little bit, that's fine. But if you're in a manufacturing setting and you have the normal conveyor belt of things and your computer is supposed to be stamping or grabbing or cutting these things that are on the conveyor belt, and your computer just decides to slow down, the conveyor belt is still going there. And so you can't slow down. You've got to keep running. Or if you are trying to land your rover on the moon and you're trying to land the rover on the moon and you're calculating and you're looking at your LiDAR images and trying to figure out where, how much thrust to put on and where to land on the moon, you can't just slow down and say, oh, wait, pause. I need to check my email while I do this. No, it's got to be done in real time. Otherwise, you crash on the moon for this. So that's real-time operating systems out there. We're not really going to be able to talk. We'll be dealing more with these non-real-time operating systems here. But we still are going to try to keep on track as much as possible here. So what does an operating system kind of do for us? We'll look at a couple key things. We kind of talked a little bit about I/O, and we'll deal more with some of the input-output things in the lab this week. We'll connect up different sensors to our Raspberry Pi. Oh, and yeah, so for Thursday, we'll have to have your Raspberry Pis here and your circuit breaker, or I mean your breadboards. And I'll bring some sensors here for you to do. I was just thinking you don't have a sensor, so if you're not going to be here on Thursday, I might want to get you a sensor before you go. So, okay. So we'll talk about that. So I/O in handling input-output devices, memory, page virtual memory, and again, this is introduced in chapter 7, so we'll do more of that in just a little bit. Again, we'll jump. That's why we're adding chapter 7 to kind of our list of things this week. We have multiple processes going on, and so we have a scheduler that is kind of keeping track of what process, what jobs, what things are running on our computer, and making sure everyone gets a fair share of time on the processors here. Device drivers, we mentioned a little bit, and interrupts. We're not going to talk too much about how they work at that low level stuff. But again, that's kind of tied to some of this. How do we interact with these I/O ports and stuff like that? So let's talk about processes and threads here. So like most of you have had Java 1 now here, and have done, or I've done kind of CS principles here. So you've done CS principles, you made an app, you've done your blocks there, and you've run your app. That generally runs in what we call one process or one thread. There's just one kind of thread of execution, one thing that starts and goes through and does things. And you don't have two things going on at the same time generally. So if you write a Java program, you start in main and you go line by line through it, and it runs line by line until it's done. If you have your app, an app is running and it is just waiting there for events there. And so if you click and you have a mouse click event there, it'll find the mouse click code and run that. But while it's running that, it can't do something else. So if you like click on one thing and do something else, or do two touches at the same time, it only is going to process one and then the other. So very sequential there. So generally most of our programs run in what we call a single process, but we might have multiple things running on our PC at a time. Like how many windows do you have open here? So I might have my Chrome browser, and I have 3 tabs open on that. I'll have Zoom opened up here, and I might have, Notepad or email, something else opened up here. So I might have multiple programs running at the same time, and each one of those is a process or a thread. And for your point of view, a process and a thread can be basically treated as the same thing. It's a unit of execution for this stuff. And we're going to be running multiple ones of these processes at a time here. These processes can be, have different states. They start up, we just initialize them when they're starting, and then they're just generally just running. But they're not all running at the same time. Some of them will be waiting on stuff. So like if I load up a web page, that web page will be just sitting there and waiting. So that thread, that process will just be waiting on, a download or the page to refresh or something like that. Some of the stuff will be blocked. So again, if I'm waiting for a keyboard input, waiting for the user to type something in, we'll talk about this thread or this process being blocked. It doesn't really have anything else to do. It's just waiting for you to type some keys and hit enter for this. So, now we're going to look at some ways where we could control these processes and keep track of them here. So we'll talk about every process that's running will have what is called a processor control block, which will be just information about it. And then we'll have some sort of part of the operating system will monitor all the processes running, and we'll be able to quit some or start other ones and see how this works. We'll talk a little bit about how we schedule these processes to work for different things. I'm not going to get into what are called interrupts in here, but we'll just look at the normal scheduling and access processes. So if you have a bunch of stuff to do, what order do you do them in? And we can think of this as like these programs we're going to run. So we have one let's assume we just have one processor with one core, can only do one thing at a time. But we are running lots of different processes, lots of stuff done. So like maybe you do the same thing. Maybe you have a to-do list for the day. And so in the morning, you'll write down the things you want to do that day on your to-do list. The question is then, what order are you going to do those in? So maybe you do kind of a first come, first serve. Whatever order you wrote them down in, you're just going to start at the top of the list and do them in order. Or whatever programs you run, you're just going to run that program till it's done and run the next one there. Those sorts of stuff works fine when you can only do one thing at a time, but often we are going to have to do multiple things at the same time. So like in our computer, we'll have different threads up and running here. And I might be playing a video in this thread while doing stuff in this thread, while loading something in this thread. So how do I do 3 things at the same time if my processor can only do one thing at a time? And what we do is we jump back and forth between these very quickly here. So we're going to multitask here, and there's some ways of doing this. Most common is kind of a round robin scheduling, where the computer will spend a little processor time here, a little processor time here, and a little processor time here, and then go back here and give everything a little processor time. And we'll switch back and forth to these tabs. That's why when I play this video, and it's in the background, you can hear it stutter. It plays a little bit and then waits for a little second, and it plays a little bit and waits for a second because of the processor running in the background. Did you hear that? That doesn't happen. So why don't we hear the video starting and stopping? Our processor is switching so fast that it can switch fast enough so we don't notice. There's not a lag for it. It's switching, 100 times a second here. So it can jump to this video and start playing a second worth of video. And then it doesn't have to get back or, even play a 1/10 of a second worth of video and send that to the video stuff and then come back and do some other stuff and come back and, oh, this 1/10 of the second video is almost done. I'm going to queue up the next 1/10 of a second video, and it can play it. So it will run smoothly, even though it's doing this and this at the same time for this. So round robin scheduling is, again, just this going back and forth through lots of different, all the different processes, making sure everything done. Now, sometimes you will notice when you're running some heavy CPU stuff that all our background tasks will stutter or will slow down or stop there. So we sometimes have priority scheduling or some other kinds of rate monitoring, so that like if we have a video that's playing, we might give that, even if it's in the background, we might give it enough, make sure it has enough priority so that the video can play smoothly regardless of what other things we're doing here for this. So there are just different algorithms for scheduling these processes and what how they work. And I'm not going to go into too much detail, but let's look at these processes and what they do here. So I'm actually going to go and make you do this by putting it in the exercise. So if I go look at the exercise for this week, so you might want to open up the exercise, make a copy of it here. We're going to look at some low-level stuff. So first, we're going to jump back and just look at some of this device management stuff. We really haven't looked at that in Windows. So the first one is just resource allocation here. So I'm going to bring up the device manager for this. So probably the easiest way to bring up the device manager is to we don't have a My Computer here. Let's just type in device manager. Okay, so you can ignore these, right click on My Computer and select properties. You can just click on Windows and start typing device, and it'll bring up the device manager here. So again, it's warning us that we can view the stuff, but because we're just a standard user, we're not going to be able to change stuff for this. So these are all the devices are broken down into different parts here. I want you to just pick one of these areas in the device manager and look at them. So I'm going to go into, and you can do this or you can do another one. I just walk you through sound, video, and game controllers. So I'm going to go into there and see what sound, video, and game controllers there are for this. There should be some audio players here. I have a hover cam. You probably don't have a hover cam. A hover cam here. Let's see, where's. I thought I had that. Yeah, I don't have it. I don't know where I dragged it. There's a little window showing my picture, so I'm actually recording that. But I have a hover cam. You probably don't have a hover cam, but you can select any of these audio files. And again, if you don't want to do that, select some of these. I want some other device display. This is our display adapter here. This is our keyboard, our monitors, something like that there. And then you can select one of these and right click and bring up properties for this. So I'm going to bring up my hover cam properties, because you don't have one of those, but you can bring up one of yours here. And this will show us properties about our device. So generally each device is mapped somewhere in memory. And so we have this location specification, we have the device type, the name. We're running device drivers here. And so again, I don't know if you do this, it's sometimes something's going wrong with your computer as well, you might be asked, you might have to update the device driver. So you might go in here, bring up the device driver, and hit update device driver. Now, you don't have permissions to do that on these machines because students tend to break things sometimes in the lab, so you're restricted. But if you were a normal user and you look at your own machine, you should be able to update the device driver, disable a device, uninstall a device for that. And all I can do is bring up the device details, and it's just telling me which files are running this device for this. So I just want you to look up, go into the device manager, pick a device, Here, again, you can certainly do this one if you want. Right click on one of the devices and show its properties and put a screenshot over here. And, so yeah, let's see. I'm going to do my hover cam. Go to drivers. And again, I always just do Windows Shift S to do the screenshot. You can do it whatever we want, but I'm just going to do that and attach it here. Okay, questions on bring up the device manager? Okay, let's do the next one, which is now what we're actually looking at in the textbook, this process manager area. So we are going to open up the task manager. You can hold down Control Shift Alt. Oh, no, Control Shift Escape should bring up the task manager. You can also, I think you can just click on here and type in task manager, start typing task manager to bring that up here. And what it's trying to show is what programs do you have running? So I have Chrome, I have Notepad, and I have Zoom. I have 3 things running here. But I might want to look at more detail. So I'm going to click on more detail and it'll bring up a much bigger view. So fewer details just shows the programs I'm running. More details brings up this more interesting view. So I'm going to bring up this more detailed view here. So this will list the processes that are running. So now I'm running Chrome, Notepad, I'm running a task manager because this is the task manager, and Zoom. There's also a lot of background tasks that are running on here. And a lot of these you probably don't even know what they are for. Sometimes it's hard to tell what they're for. Sometimes you know, like we have some Adobe software and Adobe installs lots of background tasks. So Adobe Creative or content synchronization of Adobe Crash, all this Creative Cloud stuff. I think this is all Adobe stuff running in the background. Chrome runs some extra stuff in the background here. HP is running some stuff in the background. Intel, Microsoft is running a bunch of stuff in the background here. So there's lots of stuff running in the background. And most of it is tied to software that we have installed, like VMware. We'll actually use that later on in our course, but it's a virtualization, runs virtual machines on our computer. It's actually running all the time. And so is Zoom. Well, yeah, here. And Zoom is running 2 ways. It is I'm running Zoom and recording a meeting, and I also have the Zoom console open here. So again, a lot of times you'll see little icons down in the bottom right. Some of those are tied to some of these background processes here. Okay, we're going to want to look at which processes are using the most CPU, the most memory, and the most disk space. So I would say start up some more processes here. So again, I'm running Chrome, run some other stuff there, maybe run Microsoft Word, and open up a document there. So yeah, Word, maybe run something else, whatever you know, run if you're in Java, run Apache, whatever running, some NetBeans or something like that too, and just see. So then we're going to look at what processes are using the most. So this first one is CPU, and I can just scan down and see what processes. So Zoom, for me, is using 15% because I'm recording and broadcasting this meeting. There, you'll have something else. And this anti-malware is running at 12% here. I can scroll down. If only there was some way I could sort them by the CPU usage. If, you know, you'd think they would just make it so you could just click on this and it would sort them by CPU usage, and then you could just see that. So, so just click on the CPU usage and see what are your top 3 processes. Put those in here. So for me, it's Zoom, anti-malware, and just the desktop here. But again, if let me go into Chrome, and let's play this YouTube video. I'm going to mute that, maybe there, but it's still running. So now Chrome is up there in the top 3, and particularly if I bring it up in top here, it will jump to 25% sometimes for this. So again, see, run some processes and see. Then, so once you get a top CPU, what are the top memory uses and what are the top disk usages for this? So now within Chrome, I have multiple tabs open. So if you're running multiple tabs with Chrome, I'm fine with you opening up and seeing which tabs. So some tabs will be using a lot more memory than other tabs. And then there's a bunch of just Chrome background stuff that's kind of running here. So I will see multiple Chrome things. So you can actually expand some of these things. So like Zoom, I have the Zoom hosting and my sharing the meeting stuff. So since I'm sharing the screen, that's a different thing. So fill in the top processes that are running for each of these. So that's under processes. Again, that's all the processes that are running on our computer. I can also look at just performance and see what's happening as far as the CPU usage here. I'm using 40% of my CPU about memory. I'm using 7.8 15 gigabytes of memory here. And again, if I open up new tabs and do things in Chrome, open up a bunch of new stuff here, I should see my memory, my CPU usage jump way up as I open up those tabs. My memory usage jumped up here. My disk use jumped up some. And my Ethernet, this is my network connectivity, also increased. So under performance, you can see these different things and what they're used, how much they're using. What do I ask you? Using the performance tab, display the disk usage and try some activities to increase disk usage. So you can try copying. So if I go to disk usage, I try to copy some files. So let's see if I have anything big downloaded. I don't have much. Let's see if I have anything under documents. I'm going to copy this whole Zoom folder to the desktop and see if that works. So I'm going to do this big copy. That didn't take very long. I'm trying to see what else I have. Well, the other thing is I can just try to download something from the internet. So I'm just going to go to my Google Drive here. Oops, not there, in this other page here. And go download something that's big for this. So I'm going to click on this and download this zip file. But again, as it downloads it, it should use up some disk space and also some in Ethernet space. The Ethernet is going to be much slower than the disk. So I'll see a little bump in the disk space here, but I'll see a much bigger jump in the Ethernet by network traffic as it downloads this file. Once that file is downloaded, I can then maybe make a copy of it. So if I make a copy of it, that should give me a little bit of disk space bump. So again, do something to increase the disk space. And I think, do I want a picture of it? Report how high you can get the disk space at. I don't think I got the disk space very high here. But it looks like, I think each one of these lines is 10%. So I got it above 20%, it looks like, maybe 25% of these lines. Next thing we want to look at is just what starts when we want to go back to the task manager. There's a startup tab. These are all processes that are set up to run when our computer starts up. If you ever want to optimize your home computer, you might want to look at what's in this tab and delete stuff or disable stuff that you don't necessarily need here. It's like I often disable all the Adobe stuff because I use Adobe maybe once a month and I just run it then. So I don't need all this Adobe stuff. So I might disable this here. Now, you can't disable stuff on these machines because we don't trust you to do anything here. So I can expand it, but I can't disable it here. But on your home computer or some other computer, you can do that here. So, and the startup list a process that is enabled to start up automatically. Just to pick any of these processes. So like Google Drive, HP notifications, those are stuff that's run. So the last thing we're going to do is just run some app and get some information about it. So I'm going to run Notepad. I already have Notepad here. This is Notepad. Okay, now I'm going to try to find out some information about Notepad running. So I'm going to go back to processes. I'm going to sort by name. Again, not by CPU, and then I'll show the apps that I'm running in the background app separate. Notepad will be here. I can right click on it and bring up some properties of this. I think I want to bring up this one. So, I guess I forgot. I was under process. I have to go to under details there and see this. So again, I can go under details, find my Notepad app. Where's my Notepad app? Here's Notepad running. I can look at how much memory it's using, how much CPU it's using, what its process ID is, and which user is running under it. So I can fill in that. So the name of the app you ran, the process ID is just this number. So I'm under details. Mine is 3001. So I ran Notepad, and its process ID was 3001. Yours will be different, of course. How much memory is it using? So Notepad is using 1756 for me. And I think that's kilobytes. Yeah, kilobytes. Now, if I want to check the priority here, I should be able to set the priority, and I should see it is running under normal priority for this. And we mentioned real time. Windows isn't can kind of be used as a real time, so we can set this to real time priority, which would be the highest priority, but it is just running on normal. So this is running normal. Anything you can run is probably running normal. And how can you end this process inside this task manager? So if I have this process, how do I kill this notepad? So if I right click on it, I can say end task. And it'll end this, it'll close that. So you can right click and select end task to kill any process. I assume you do, well, you do this sometimes when some process hangs, you bring up the task manager or something like that, and you right click on, kill some processes that are just stuck running. If you don't, I mean, this is a pretty common thing. When you have some program that's just frozen, you can try to just use this to kill it. It's similar to, again, if it's running down here in my start bar or whatever bar here, I can right click there and show close window, and that'll do something similar, although sometimes the task manager will be able to close things when this might not be able to. Okay, so we learned all the process. I'm always amazed how many processes Windows runs in the background, especially some people who have installed lots of junk software on their computer. They have hundreds of background processes running for all this sort of junk. So if you're ever interested, if you ever see someone's computer and they say, "Oh, can you help me? My computer's so slow," you can just look at the background thing and see how much stuff is starting up here, and just get rid of a bunch of that stuff. So, okay, questions on this before I move on to the next part? Okay, I'm going back to the textbook. So again, the computer is cycling through all these processes, all the programs I'm running, it's cycling through them, and all the background processes that are running here, because again, as network traffic goes in, or if I'm sending things through a printer, or I'm watching the keyboard input, all that stuff has to be handled by this one processor that's running for this stuff. Now I can also view this stuff through this resource monitor and look at how that works. That's particularly handy when I'm trying to get a better idea of some of this things like CPU usage and threads and some more details. So let's look at the resource monitor. It's the last thing here, I think, in chapter. Let's see. Oh no, we have to go multi-process. Well, we'll do the resource monitor because I think that's the next thing here. So I did process manager. Step 3 is resource manager. So resource monitor. So I'm gonna click on Windows, type resource, and click resource monitor. Oh, you gotta be kidding. We can't bring up the resource monitor anymore. That's sad. Okay. Okay, so we're gonna have to skip step 3. So step 3, you're gonna highlight it and just cross it out. I'm gonna have to just explain it to you then. Stuff. Okay, so with the resource monitor, you can just see a little more details of what things are doing and multiple threads. So let's just talk about processes and threads a little bit. So in the resource monitor, you'll see something called threads here. And so some of your programs will run multiple threads. And so like, it's not uncommon, like when you get to maybe a more advanced programming course and you are like going out to the internet to do something, you will create another thread in your code. You'll just say new thread. And in that new thread, you will have it go out to the internet and wait for the response while your main program can do something else here. So it's not that problem for us to create a program that might have 2 or 3 threads running sometimes. And now advanced programs might have a dozen threads running at once for this here. So we might, each process might have multiple threads inside of it, and each thread is given a certain amount of time. So actually each process is given an amount of time, and then your process has some control over which threads are running. So inside your code, you might run one thread, and then you might say, this thread is done, allow other threads to run. And there's commands like await, or listen, other commands. And again, it varies a lot from language and environment, but one thread can pause and give other threads time to do things for that. And we're not going to get into that, but just know that threads can the process can handle which threads are in, or if you want to have multiple threads sometimes running at the same time. So now with Linux, we're going to try to do some of this stuff on Thursday, but you can look in Unix, you can do something similar, but look at what processes are running. Every process, again, will have a process ID. There'll be the user that's running it, the priority, and where it's running, percent of CPU, percent of memory that's running, and stuff like that, and then the actual program that's running. So we'll be able to see this on Thursday a little bit when we get our Raspberry Pis up. Let's talk multi-processing here. So it's possible to have a computer with multiple CPUs running there. A common project sometimes with Raspberry Pi, since they're kind of inexpensive, is to kind of make a cheap supercomputer with Raspberry Pis, where you might get 8 Raspberry Pis, put them all together in one control unit, so they act as one I don't know if I call it a supercomputer, but one multi-processor computer there. So you can do that. But today it's much more common to have multi-core processors. So rather than having 8 CPUs, most of our CPUs have multiple processors or core in them. So they can be doing 8. It's like we have your CPU has 8 CPUs or 8 cores inside of it, can be running 8 separate sets of instructions at the same time there. Now, if you're only doing one thing at a time, like you're only running Notepad and typing in the Notepad, you're not going to be able to run all 8 cores, because there's really only one thing for the computer to do often, and that's just, display something on the screen when you type it there. So this only works when you're running multiple processors or multiple processes or multiple threads there, and then your scheduler that's looking and seeing, giving every process some time, will schedule processes on different cores, and it gets more complicated for that. So again, most of this is running this multiple instruction, multiple data architectures here. Again, that means that we can be running multiple instructions at the same time and reading data from multiple locations at the same time here. So just know that most computers today, I don't know, what are we at 4 or 8 cores? That's what I thought we were. Is that still pretty common? 4 cores on a CPU? Has anyone bought a CPU computer lately and looked at that? So does that sound about right? So for this. Okay, that wraps up 5. I'm going to play a video so I get to stop talking here. And then I want to turn on the volume. Okay. This is one of these simplistic crash course computer cores, but I think it does a good job at kind of giving you again a reminder of the basics of these computer systems. Or let's see how our volume is doing here.
Yeah, computers in the 40s and early 50s ran one program.
And it goes lots of history, which I like because I'm old. So you have to put up with my history of fascination.
Then they'd carry it to a room containing a room-sized computer and hand it to a dedicated computer operator. That person would then feed the program into the computer when it was next available. The computer would run it, spit out an output and forth. This very manual process worked okay back when computers were slow, and running a program often took hours, days, or even weeks. But as we discussed last episode, computers became faster and faster and faster, exponentially so. Pretty soon, having humans run around inserting programs into readers was taking longer than running the actual programs themselves. We needed a way for computers to operate themselves, and so operating systems were born. Operating systems, or OSs for short, are just programs, but special privileges on the hardware let them run and manage other programs. They're typically the first ones to start when the computer is turned on, and all subsequent programs are launched by the OS. They got their start in the 1950s as computers became more widespread and more powerful. The very first OSs augmented the mundane manual task of loading programs by hand. Instead of being given one program at a time, computers could be given batches. When the computer was done with one, it would automatically and near instantly start the next. There was no downtime while someone scurried around an office to find the next program to run. This was called batch processing. While computers got faster, they also got cheaper. So they were popping up all over the world, especially in universities and government offices. Soon people started sharing software, but there was a problem. In the era of one-off computers like the Harvard Mark I or ENIAC, programmers only had to write code for that one single machine. The process of punch card readers and printers were known and unchanging. But as computers became more widespread, their configuration was not always identical. Like computers might have the same CPU, but not the same printer. This was a huge pain for programmers. Not only did they have to worry about writing their program, but also have to interface with each and every model of printer and all devices connected to a computer, or called peripherals. Interfacing with early peripherals was very low level, requiring programmers to know intimate hardware details about each device. On top of that, programmers rarely had access to every model or peripheral to test their code on, so they had to write code as best they could, often just by reading manuals, and hope it worked when shared. Things weren't exactly plug and play back then, more plug and pray. This was clearly terrible. So to make it easier for programmers, operating systems were implemented as intermediaries between software programs and hardware peripherals. More specifically, they provided a software abstraction through APIs called device drivers. These allow programmers to talk to common input and output hardware, or I/O for short, using standardized mechanisms. For example, programmers could call a function like print high score, and the OS would do the heavy lifting to get it onto paper. By the end of the 1950s, computers had gotten so fast they were often idle waiting for slow mechanical things like printers and punch card readers. While programs were blocked on I/O, the expensive processor was just chilling, not like a villain, just relaxing. In the late 50s, the University of Manchester in the UK started work on a supercomputer called Atlas, one of the first in the world. They knew it was going to be wicked fast, so they needed a way to make maximal use of the
Wicked fast. That's really fast, in case you don't know what that term wicked means. It's an old colloquial.
Those programs automatically, like earlier batch systems, but could also run several at the same time on a single CPU. It did this through clever scheduling. Let's say we have a game program running on Atlas, and we call the function print high score, which instructs Atlas to print the value of a variable named high score onto paper to show our friends that we're the ultimate champion in virtual TV. That function call is going to take a while, the equivalent of thousands of clock cycles, because mechanical printers are slow in comparison to electronic CPUs. So instead of waiting for the I/O to finish, Atlas instead puts our program to sleep, then selects another program that's waiting and ready to run. Eventually, the printer will report back to Atlas that it finished printing the value of high score. Atlas then marks our program as ready to go, and at some point, it will be scheduled to run again on the CPU. and continue on to the next line of code following the print statement. In this way, Atlas could have one program running calculations on the CPU, while another was printing out data, and yet another reading in data from a punch tape. Atlas's engineers doubled down on this idea and outfitted their computer with 4 paper tape readers, 4 paper tape punches, and up to 8 magnetic tape drives. This allowed many programs to be in progress all at once, sharing time on a single CPU. This ability, enabled by the operating system, is called multitasking. There's one big catch to having many programs running simultaneously on a single computer though. Each one is going to look to memory, and we can't lose that program's data when we switch to another program. The solution is to allocate each program its own block of memory. So for example, let's say a computer has 10,000 memory locations in total. Program A might get allocated memory addresses 0 to 999, and program B might get 1,000 through 1,999, and so on. If a program asks for more memory,
So we'll be jumping into units, chapter 7 after this, and this deals a lot with memory allocation. So this is kind of where I want to watch this for.
grant that request. And if so, what memory block to allocate next? This flexibility is great, but introduces a quirk. It means that program A could end up being allocated non-sequential blocks of memory in, say, addresses 0 through 999 and 2000 through 2999. And this is just a simple example. A real program might be allocated dozens of blocks scattered all over memory. As you might imagine, this would get really confusing for programmers to keep track of. Maybe there's a long list of sales data in memory that the program has to total up at the end of the day. But this list is stored across a bunch of different blocks of memory. To hide this complexity, operating systems virtualize memory location. With virtual memory, programs can assume their memory always starts at address 0, keeping things simple and consistent. However, the actual physical location of computer memory is hidden and abstracted by the operating system. Just a new level of abstraction. Let's take our example program B, which has been allocated a block of memory from address 1000 to 1999. As far as program B can tell, this appears to be a block from 0 to 999. The OS's CPU handles virtual to physical memory remapping automatically. So if program B requests memory location 42, it really ends up reading address 1052. This virtualization of memory addresses is even more useful for program A, which in our example has been allocated 2 blocks of memory that are separated from one another. This too is invisible to program A. As far as it can tell, it's been allocated a continuous block of 2,000 addresses. When program A reads memory address 999, that does coincidentally match the physical memory address 999. But if program A reads the very next value in memory at address 1000, that gets mapped behind the scenes to physical memory address 2. This mechanism allows programs to have flexible memory sizes called dynamic memory allocations that appear to be continuous to them. It simplifies everything and offers tremendous flexibility to the operating system in running multiple programs simultaneously. Another upside of allocating each program its own memory is that they're better isolated from one another. So if a buggy program goes awry and starts writing gobbledygook, it can only trash its own memory, not that of other programs. This feature is called memory protection. This is also really useful in protecting against malicious software like viruses. For example, we generally don't want other programs to have the ability to read or modify the memory of, let's say, our email. With that kind of access, malware can send emails on your behalf and maybe steal personal information. Not good. Atlas had both virtual and protected memory. It was the first computer and OS to support these features. By the 1970s, computers were sufficiently fast and cheap. Institutions like a university could buy a computer and let students use it. It was not only fast enough to run several programs at once, but also give several users simultaneous interactive access. This was done through a terminal, which is a keyboard on screen that connects to a big computer, but doesn't contain any processing power itself. A refrigerator-sized computer might have 50 terminals connected to it, allowing up to 15 users. Now,
So when I was in middle school and high school, there was one computer in Minnesota in Mankato that each high school was connected to, and we had one terminal in our school that was connected. Well, actually, we had 2 terminals in our school that was connected to this computer in Mankato. And you could log in and do stuff, and like you could do this processes and see, and you could see, well, this not only process that you were doing, but all the processes, every student in the state, there might be a dozen students at different spots in the state connected to this computer running things there. So that was these early days where we had one computer in the state. There were more, but that was only one computer that schools were using.
Time sharing. With time sharing, each individual user was only allowed to utilize a small fraction of the computer's processor memory and so on. Because computers are so fast, even getting just 1/50 of its resources was enough for individuals to complete many tasks. The most influential early time sharing operating system was Multics, or Multiplex Information Computing Service, released in 1969. Multics was the first major operating system designed to be secure from the outset. Developers didn't want mischievous users accessing data they shouldn't, like students attempting to access their final exam on their professor's account. Features like this meant
So when I was in college, we had a shared computer system, which we all used. I'd go to the library and there would be, we didn't have computers like this, but we had screens. So we had like 15 screens around connected to our shared computer on campus. But if you knew what you're doing, you could look at any spot in your memory and print out the text or whatever with the program at any spot in your memory. But if you're accidentally, like, instead of saying memory location 0 to 100, if you said like memory location 0 to 10,000, it would show your memory and all the other memory of everyone else on the computer, especially if you went from like minus 1,000 to plus 1,000 memory. You could look at everyone's memory because there wasn't any security in place. So some bad programmers would probably, like on Friday in the evening when everyone was working and trying to do their assignments, some bad programs were probably able to just look at everyone in the lab's memory and just see everyone else's computer memory and what they're programming. That's the problem with not having memory protection.
Multics was really complicated for its time, using around 1 megabit of memory, which was a lot back then. That might be part of a computer's memory just to run the OS. Dennis Ritchie, one of the researchers working on Multics, once said, one of the obvious things that went wrong with Multics as a commercial success was just that it was sort of over-engineered in a sense. There was just too much in it. This led Dennis and another Multics researcher, Ken Thompson, to strike out on their own and build a new lean operating system with Unix. They wanted to separate the OS into 2 types. First was the core functionality.
So Unix came out when I was in college, and we got a computer that ran Unix, and I have a book, and I was gonna bring it down, I forgot. I have the book that's the Unix book that Ritchie and Thompson wrote at Bell Labs about this. So this came out when I was in college.
Things like memory management, multitasking, and dealing with I/O, which is called the kernel. The second part was a wide array of useful tools that came bundled with, but not part of the kernel. Things like programs and libraries. Building a compact lean kernel meant intentionally leaving some functionality out. Tom Van Vleck, another Multics developer, reported, I remarked to Dennis that easily half of the code I was writing in Multics was error recovery code. He said, we left all that stuff out of Unix. If there's an error, we have this routine called panic. And when it is called, the machine crashes and you holler down the hall, hey, reboot it. You might have heard of kernel panics. This is where the term came from. It's literally when the kernel crashes, has no recourse to recover, and so calls a function called panic. Originally, all it did was print the word panic and then enter an infinite loop. This simplicity meant that Unix could be run on cheaper and more diverse hardware, making it popular inside Bell Labs where Dennis and Ken worked. As more developers started using Unix to build and run their own programs, the number of contributed tools grew. Soon after its release in 1971, it gained compilers for different programming languages and even a word processor, quickly making it one of the most popular OSs of the 1970s and 80s. At the same time, by the early 1980s, the cost of a basic computer had fallen to the point where individual people could afford one, called a personal on-home computer. These were much simpler than the big mainframes found at universities, corporations, and governments. So their operating systems have been equally simple. For example, Microsoft's disk operating system, or MS-DOS, was just 160 kilobytes, allowing it to fit, as the name suggests, onto a single disk. First released in 1981, it became the most popular OS for early home computers, even though it lacked features like multitasking and protected memory. This meant that programs could and would regularly crash the system. While annoying, it was an acceptable trade-off, as users could just turn their own computers off and on again. Even early versions of Windows, first released by Microsoft in 1985, and which dominated the OS scene throughout the 1990s, lacked strong memory protection. When programs misbehaved, you could get the blue screen of death, a sign that a program had crashed.
So have you guys had the blue screen of death before? Yeah. Now it's harder with Windows 10 and stuff, to crash the whole operating system, but you can still crash the whole operating system at times. There.
So badly, it took down the whole operating system. Luckily, newer versions of Windows have better protections and usually don't crash that often. Today, computers run modern operating systems like Mac OS X, Windows 10, Linux, iOS, and Android. Even though the computers we own are most often used by just a single person, you, their OSs all have multitasking and virtual protected memory, so they can run many programs at once. You can watch YouTube in your web browser, edit a photo in Photoshop, play music in Spotify, and sync Dropbox all at the same time. This wouldn't be possible without those decades of research and development of operating systems, and of course the proper memory to store those programs, which we'll get to next week. I'd like to.
Okay.
I picked the software engineering programming.
Okay. Let's jump to a little bit of 7. How are we doing on time? I want to make sure we have time for the exercise, the next thing. Okay, just a quick thing. All computers today work on what's called the von Neumann architecture, which is well-known architecture, a processor with memory, a control unit, registers, and ALU here, and input and output devices there. And we're still using this from the 50s sort of view, and we haven't, there's now proposed versions that are different than this. But again, and we've got now multiple CPUs and multiple cores and some adaptations of this, but again, this is often what we're seeing still. I'm gonna not skip over this architect, just get down to this physical and virtual memory. So again, we have RAM out there. RAM used to, we can't run out of RAM depending on what you're running on your computer. So if you're running multiple things at the same time, you can run out. Now, it doesn't matter how much you have stored on your computer, that's your disk space. But when you're running a program, it loads it up in the memory and runs it. And so if you're running multiple tabs at a time and multiple programs at a time, all that is fitting in RAM at the same time. And so if you're running lots of different, if you have lots of tabs open and lots of different programs open down here, you can be running out of RAM for this. It was more common when RAM was more expensive. Now it's getting cheaper here. Now, in order to manage this, we use something called virtual memory. So we use part of your hard drive as overflow memory there. So we break memory up into pages, and then we keep so much in RAM, but if we need to bring more stuff in the RAM, there's not space, what we'll do is we'll copy a whole page of memory onto your disk and use that. So on your disk is something called a page file or a virtual memory file. It's a big file that is just used by operating system to store pages of memory out there and pull them back in. It's like an extension of memory for you to use. And we swap pages back and forth with different algorithms here. So that's what we're going to look at today, is this page virtual memory, where again, we have these pages in memory and we'll swap pages in and out. So some pages you'll have limited amount of space in RAM, and then you'll have to access more things and you'll have to write those to your page file. So that's what we're going to do here for this. Why don't we, let's see, I have 5 decks of cards. So you're going to have to work in groups to share the 5 decks of cards here. So we'll get a deck of cards. You'll get a deck of cards. Let's see you can decide where. So we only have 5 decks of cards. So find a nearby deck of cards and befriend that person there. Okay. Now, you also need, we're going to have the simulation, you need a page file and some RAM. Okay, and then you're gonna wanna set up, you can see on the picture how you wanna kind of set this up. So here's your page file and RAM picture. So what we wanna do is just to keep track of things, set your page file, label on top and your RAM on the bottom. And then you want to load, we're going to run one program, the club program. So you're going to find all your clubs and load it in. You have 12 slots. So make sure you have enough space in your area to put 12 cards down here. If you have multiple people, you can actually separate this. So this can be one person and this can be another person. You can separate it this way. So you just need a page file. Someone needs to be in charge of the page file. Someone needs to be in charge of RAM. And the one rule is RAM only has 12 spots in it. So when we're going to load in the 12 clubs into that spot. Okay, so you got your clubs loaded up in the RAM. No, sort of, just as all clubs. It can be in any order, I guess. Just so that you can keep the jokers. So again, we want all the clubs down here, and then the rest of the cards are part of your page file here. So again, if you have multiple people, I would put one person in charge of the page file, another person in charge of RAM, so we can do that. Now, what I'm going to do is we're going to be running different programs, and these programs are going to need different things. So right now, everything, we have all this memory. Well, we have a bunch of virtual memory, our page file, we have a bunch of RAM, we can store 12 things at RAM, but we might need access to other things. So the first thing we're going to do is we need to find the 3 of hearts. And we need to put that into our page file. I just sort your cards by suit. Doesn't hurt my head. So if you feel the need to do that, that doesn't hurt. Whoever's doing this page file. Also, so what you want to do is you want to find the 3 of hearts and bring it into memory, and then you can pick whoever's in charge of RAM can put it in any spot, and then take whatever, like, let's say you wanted to replace the 7 of clubs, you would take 7 of clubs, put the new card there, send the 7 of clubs back into the page file, the virtual memory, there. So again, you only have 12 spots in memory, and you can swap one. So, yeah, so you might want to, you can see your 12 spots a little more. You'll only have 12 spots here. So this one, now you have to put this somewhere in one of these spots.
So.
And, yeah, so.
Yeah.
You in charge of all these other parts. You are. Grants. You're gonna be.
Yeah. Like.
You're gonna be virtual memory, so then you're gonna give them. So, yeah, 12.
So when we scroll down, that's,
Okay, so you're gonna find the 3 parts.
so we have that.
Give it to him. Put it in one of your slots, and whatever slot you're gonna replace, give him that one.
Start this.
Okay, so you write that there, and then you have. Okay, good. Okay, so then you're gonna get the 4 parts and put that in some spot. Okay? Right, yeah, so when you like pick up the 4, like, let's see, you've done the 3 and 4, now you do the 5, slide the 5, put it here, and then whatever's here, put it back. Okay?
Yeah, it looks like those were.
So, yeah, you wanna have 12.
Yeah.
Hours here eventually.
Yeah,
Or did you do that already?
we did it the first time, let's do the second.
The second, okay. So we wanna swap, move the 3 of hearts in the memory, the 4 of hearts, the 5 of hearts, 6 of hearts, 7 of hearts, 8 of hearts. Each of those are gonna go in memory and they're gonna have to replace maybe a club, maybe one of the earlier hearts, anything like that. But, just so you know, later on, we're gonna need the 4 of spades, the 5 of spades, 6 of spades, 7 of spades. So we're gonna swap those in, and then we're gonna need the 2 of clubs again and 3 of clubs. So keep swapping them in and out. And what we want to do is minimize our swaps. So there might be times where the 2 of clubs might already be in memory, so you don't have to swap it in the memory. So you want to try to not swap. So if you're gonna need the 2 of clubs, hopefully you haven't swapped that out already, and it's 3 of clubs. Or like here, if you need the 7 of hearts, maybe it's still around from before, or maybe you swapped it out.
Yeah, if they're not. Sometimes how many stars are part of that? Rob says, right?
Oh.
Okay, so you just swap them. Yeah. His. Yeah. We can switch out. You want to do all the hearts first?
Yeah.
Oh, Tim, we can take a picture.
Yeah.
You should do this. Take a picture. This was supposed to have the ones set up by the edge file.
Yeah. Okay, that makes sense.
Oh, I think it's true. They. Okay.
Should we just replace it with like something else?
Sounds good. So in operating systems, it's called something called the page replacement algorithm, where if you need to bring a page into memory, which page you put back out in virtual memory, and how do you pick a good page so that you can reduce the number of swaps. After you do this, take a picture of how your virtual memory looks. You probably have a bunch of clubs, maybe some hearts, maybe still some spades. I don't know, depending on how you selected pages here. And then we're gonna try, I'm gonna give you a set of new cards you haven't seen before. You're gonna count how many times you have to swap to get all those cards in memory. So here, you can just highlight this. Let me bring this up a little high. So you can just turn this so it's not black highlighted. And these are the cards. So once you're done with the first part, take a picture of that to put in here. And then you want the 7 of hearts, the 8 of hearts, the ace of clubs, and the 2 of clubs. See if you have those in your memory, or if you have to do a swap to get all of those in memory.
I don't know if we need to put a sticker again.
Keep separate.
Then.
Yeah.
I do.
I'm gonna just go over the last thing and then we'll be done for the day. So if you get this good, you're good. The last part we're gonna talk about is buffer overflows. You may have heard of a website called Stack Overflow, where people post computer questions and get answers. That comes from a common exploit where your stack overflows and hits the rest of your operating system here. Inside your computer's memory, there's usually memory. We often have some of it loading from the top and some of it loading from the bottom. And so usually your operating system and what's called the stack is at the top of your memory. And as we need more stack, we slowly go down in memory. And then your program that's running, the text and the data and local variables are in what's the bottom part of memory. And your local variables are in what's called the heap. And as you declare more local variables or use up more variables, this heap will grow here. And it is possible to write a program where the heap grows and hits the stack or overwrites the operating system itself for this here. Now, a lot of operating systems have protections to keep you from doing this, but it's a common exploit that you will work on. You'll declare or run some program and you'll set it up so the heap overwrites the stack, and then that'll let you run or change how your program works or executes here. So this is called a buffer overflow or a stack overflow. I just want you to find a definition of stack and heap in terms of Stack Overflow. So you can go to this article and find definitions in this article, or if you want to just use AI, ask AI, but give it in this context. I just don't want a general term for stack and heap, but I want it in kind of in terms of this exploit or this security problem. If you get this exercise good done, we're good for the day. I just need, as you go out today, turn in your cards or leave them there. You can get them back in their packs. That helps me. And on Thursday, we'll do some more Raspberry Pi stuff. Thanks.